Hey guys, welcome back to our flipped video lessons. So by now, we should be really solid on being able to solve an individual single variable linear inequality. So what we're going to move on to now is what happens when we take two of those single variable linear inequalities and stick them together. Well, what happens is we have something that we call a compound inequality, right? So we're going to dive right into this, and in the last video, like I said, we learned how to solve this one individual single variable linear inequality, and we're going to find out what happens when we put two of them together. Well, a compound inequality is just that, two single variable linear inequalities, but they're joined together by the words and or. Both of these words we use in the English language to put two things that previously didn't have anything to do with each other together in a sentence or a phrase. Okay? But they do it in different ways, right? Just like glue and tape combine things together differently. If you're trying to fix a piece of paper that you ripped, you're not going to use glue, you're going to use tape because that's the best for that situation. Now, if you broke a heel off your shoe or you broke the side view mirror off your car, not that that ever happened to me 4 times, but you're going to want to use glue to stick that back on, not try and just wrap it up with duct tape, because trust me, when it rains and snows, the duct tape comes right off. But that being said, just like there's times we want to use tape and there's times we want to use glue, and there's different ways that they're used and they function differently, and in or, while they accomplish the same thing of combining our inequalities, do it in different ways. So what we're going to do in this video is just look at what does it mean to combine two inequalities with the word and what does it mean to combine the two inequalities with the word or. So first we're going to start talking about our and compound inequalities, right? If we use the word and in a sentence, like this sentence here, Rosie said she was going to dinner and a movie. For Rosie to be true, for Rosie's statement to be true, what has to happen? Well, what has to happen is she has to go to both the dinner and the movie. If she only goes to dinner, or she only goes to a movie, or does neither, she was not telling the truth. If both, it's either both or it's nothing, right? And that's what we got to think about with the word and here. Now, when we look at an and compound inequality, the set of solutions, the set of numbers that make the inequality true, is called an intersection. So this is a vocabulary word that we've got to associate with an and compound inequality, and intersection. Where do you hear the word intersection in real life? What do we think of? Well, if you're not driving yet, you might not think about this, but I think most people would think about two roads causing an intersection. So our next question is, when is a car actually in the intersection? And the answer to that is, the car is in the intersection when it's on both roads at the same time. It can't just be on one road or the second road. It's got to be on both at the same time, or it's not in the intersection. Again, it's both or nothing with an intersection, and that's how that relates to the word and there. So, when is a number in the intersection of an and compound inequality, where we're going to carry over this same idea, that when it's a solution, it's in the intersection when it's a solution to both of the individual linear inequalities that we're putting together at the same time. Just like the car has to be on both roads at the same time. Just like Rosie has to perform both, going to a dinner and a movie, for our numbers to be a solution, they have to be on the graphs, to be in the intersection of both inequalities at the same time. So, to sum up kind of what we talked about here, when we see an and compound inequality, the solution is an intersection, which means we are going to look for where the inequalities, the graphs of the inequalities, overlap. That's going to be giving us our intersection, right? Is where we overlap. It's kind of another word when we have two roads that intersect, they kind of overlap each other. So let's take a look at some examples here. So we have x is greater than 4 and x is less than or equal to 13. So if we graph this here, we're going to graph an open circle at 4, and it's greater than 4, so we're going to graph all of those numbers to the right. And then we're going to put a closed circle at 13 and graph all of the numbers to the left. And what we're looking for is which numbers on that number line are part of both graphs at the same time. are solutions to both inequalities at the same time. And we can see that the numbers in between 4 and 13, and including 13, fit the intersection. Anything greater than 13 is only on one graph, and anything less than 4 is only on the other graph. Okay, so in our second example here, x is less than 2 and x is less than -5. Again, both open circles, both of them going to the left of 2 and -5 there. Where is the intersection? Where are the numbers on both graphs at the same time? Where do the graphs overlap? These are all things we can be asking ourselves to identify our solutions to the compound inequality. And we can see that all of the numbers less than -5 are going to be on both graphs. That's where the graphs overlap. They're going to be solutions to both inequalities there. The numbers in the middle between -5 and 2 are only part of one graph, the solutions to one inequality, and the numbers greater than 2 to the right of 2 aren't a solution to any inequality, so we don't even care about them at all. Okay, so this is our compound inequality with the word and, our and compound inequality. We're looking for an intersection, which means our solutions, the numbers have to be solutions to both inequalities at the same time, and that's going to be where the graphs overlap. This is all language we're going to keep using in class, we want to become familiar with, right? So next up is the OR compound inequalities. But before we get to that, let's take a little break here and go to chainsaw. Okay, now back to math. So an OR compound inequality, right, is going to be a little bit different. If we change the word OR in our sentence, it's going to change the meaning. So Grace said she was going to a dinner or to a movie, right? Now, what has to be happening for Grace's statement to be true? Well, she could go to dinner and not a movie. She could go to a movie and not a dinner. Or she could actually go to both and her statement would still be true. She just has to do at least one of them, right? And what that is telling us is that our solution set is no longer an intersection. We're no longer having to do both. We have to do at least one. And so we're going to have to change the name of the solutions for an OR compound inequality. And an OR compound inequality, the solution set is called a union. So again, what do we think of when we hear the word union? Well, in the work world, you probably think of working unions. Unions, and one of the most influential ones in your life is the teacher union. Every teacher you have at Grayslake Central High School, and that you had pretty much throughout all of your time in school, is part of the teacher union. Now, to be a member of the teacher union, you have to teach, and this is a shocker, I know, at a school. You have to teach at least one school. So, every teacher at Grayslake Central High School is in the union. Every teacher at Grayslake North High School is in the union. Now, we do have some teachers that teach at both schools. They travel between the schools. Well, guess what? They're in the union just the same as the teachers that only teach at one school. It doesn't matter if you teach at 2, 3, 4, 5, 6, 7, 8, 9 schools at the same time. All that matters is, do you teach at least one? If the answer is yes, you're in the union. And that's what we're going to have to think about with our numbers on our number line here. So when is a number in the union of an OR compound inequality? When it is a solution to either of the individual inequalities. We are going to include every solution to either inequality in the union, in the solution of our compound inequality. So to sum this up, when we see an OR compound inequality, the solution is a union, which means any value from either inequality's graph is a solution. Now we got to make sure we're keeping these straight. We're no longer looking for an intersection. We're taking any value on the number line, which is a part of either of the graphs of our inequalities. So let's look at some examples here. X is greater than 5, or x is greater than or equal to -4. So we've graphed both of these. Now before, if we were looking for a union, we were looking for the intersection. Now I just want to shade, I want to take every number that is part of either graph. So we're going to take every number that is greater than 5, and we're going to take, along with that, we're going to take every number that is greater than -4. All of those numbers are going to be part of the solution, because any of those numbers will make at least one of the inequalities true. It doesn't have to be both anymore, it has to be at least one. So we can see in our other example here, x is less than or equal to 6, or x is greater than 51. Again, we're not looking for an intersection. You can see every number that's less than -6 will make one of the inequalities true, and every number that's greater than 51 will make another inequality true. So they are part of the union. Think of the teachers on the left, the numbers on the left are the teachers at Grayslake Central, the teachers on the right are the teachers at Grayslake North. They're all teachers, they teach at a school, so they're all part of the union. They're part of the solution of our compound inequality. Okay, so one more thing to talk about before we get to practice here. We've talked about ninjas in math before, right? Well, there's a ninja in our compound inequalities. There will be times where we will have a compound inequality, but we will not see a word and or. Right? We can see this in this example. We know this is a compound inequality because it has two separate inequality symbols in the same algebraic inequality sentence here. So what do we do if we don't see a word and we don't know whether it's an and, looking for an intersection, or an or, looking for a union? Well, what we do is we always assume that it's going to be an and. And what we have to do is we have to take whatever is in the middle of that inequality and split it in two. Which brings us back to the chainsaw, cutting those compound inequalities in half. And now back to math. So you see what we have to do is we have to cut those, that inequality, the x, kind of into two and use it twice and stick the word and in between it. Okay, this is like a ninja here, like our ninja coefficients or our ninja operations or our ninja denominators. This is our ninja compound inequality and, right? So you can see when I graph it then, we would follow the same rules we had with an and. We're looking for the intersection, and we see that the numbers that are solutions to both inequalities, that are where the graphs are overlapping, is in between -3 and 29 there. Okay, so we've talked a lot about our compound inequalities, and if you've got questions, please come to class so that we can talk about them here. But let's do some examples together now. So we can see in our first example we've got our ninja. So we got to bust out our chainsaw and cut our inequality in half, because we've got x is greater than -8, but we also have x is less than 9. And we're looking for an intersection because this is an and compound inequality, so the intersection where the graphs are overlapping is in the middle. Okay, so in part B here, you can see we again have an and compound inequality. So I'm looking for the intersection. I'm looking for where the graphs overlap. Less than 16, also less than or equal to 19. And we can see that the graphs overlap less than 16 there. So as we move to C and D, we now change our word. We're now not an and, we're not an intersection, now it's an or, now it's a union. So as I graph both of these, we can see every number that's greater than or equal to 5 or less than 17. Well, that covers every single number on the number line. So our answer really is all real numbers. Any real number on the number line will make at least one of these inequalities true. Doesn't have to be both, just at least one. Okay, so D here, we have x is less than or equal to -7 or x is less than 9. So I take every number that's less than -7 and every number that's less than 9, and they are all included in our solution, in our union, because every number there makes at least one of those inequalities true. Okay, so we've done a couple together here. So now I want you to try some of these on your own. So go ahead, pause the video, and try these on your own now. Okay, let's see how you did here. So hopefully in the first one, you would have gotten all real numbers here, all real numbers, the entire graph. On the second one, we would have been shading the values between 1 and 9. On C, we're looking for an intersection. This can be a little tricky. We're looking for an intersection. Where do those graphs overlap? Where is there a number that is on both of those graphs that makes both inequalities true at the same time? And there isn't one. We can see that from the graph. There isn't a single number that will make both of those true at the same time, so it's no solution. And our last one is an or, a union, and we're looking for every number that's greater than -6, along with every number that's greater than 51. Well, hopefully we're understanding this a little bit, but if you have questions, please bring them to class. Oh, but wait, we're not done. We got 2 more for you to work on. And this is what we want you to do because we want to check to see if you really did this on your own or whether you just copied the notes down. And since we're trying to see that, we're not going to give you the answers. So you need to do these 2 problems. You got to have these problems done if you want to get credit for having the notes done in class. We'll give you the answers to these in class so you can check, all right? Well, that brings us to the end. I know this was a long video. Thank you very much for listening to me. And until next time, watch out for the chainsaw! Ah! Ah!